Okay, in this presentation we're going to look at inference procedures and hypothesis testing. So this is a quick worked example. Now what I'm going to do is assume that you have a bit of a background in hypothesis testing and that you're familiar with the processes and the steps involved in the hypothesis test, and that you know how to use tables to find critical values and so on and so forth. So in this particular question, we're going to just use it just to sort of pick up on the way that what could happen in a particular question. So the standard deviation of the life of a particular brand of ultraviolet tube is known to be S equals 500 hours. Okay, that starts us off fairly nicely. Okay, S is 500 hours. It is also assumed, but not known, that the operating life of the tubes is normally distributed. Okay, so it's assumed, okay, that it's normally distributed. That's the best we can do in this particular instance. If not, we're sort of stuck. We can't really go any further. So we just have to sort of work on the basis that it is assumed to be normally distributed. Now, the average tube life is 9,000 hours according to the manufacturer. So that is our, under the null hypothesis, that is going to be our our expected value under the null hypothesis. So test this claim at a 5% level of significance against the alternative hypothesis that the mean life is not 9,000 hours, and we're given two pieces of information. We're given a sample size of 10, which essentially means a small sample, okay, and a X bar of a mean operating life of a sample of 10 has 8,800 hours, okay. So just as a quick remark, this particular question sort of sets up a two-tailed test, but actually down the line you might sort of get a variant of this test which suggests one-tailed, which is to say that the mean is less than 9,000 hours. So we're going to take the easy road in that one, and just a sort of very simple construction of simple way of looking at the hypotheses. Okay, so let's get into our 4 steps. So the 4 steps are as follows. So if you're not familiar with these 4 steps that I sort of favor, not that you have to do it, but it does sort of make this process much easier to work with. So essentially state the null and alternative hypothesis. That's the null there, and that's the alternative there. That's how we denote them. Okay, mu is equal to 9,000, or really I should say hours. Mu is not equal to 9,000. Now it's actually also helpful to put in a little descriptor there about what the null and alternative hypotheses are. You know, you could put a little bit more detail than I did there, but mostly you get the gist of it there. Okay, so I'm going to move on. Now the next part here is actually the standard error, and this is not actually related to the hypotheses at all. Okay, so essentially what we're going to do is set ourselves up to find the test statistic. Now the observed difference is minus 200 hours. That's 8,800 hours minus 9,000 hours. And what that observed difference is the observed value, the observed mean, minus the expected mean according to H0. Okay, so that's a key component of the test statistic. Okay, so that's actually the test statistic there. So the observed difference is minus 200 hours. Okay, and the test statistic is as follows. That's usually given in the back of the exam paper, but in a lot of cases you might have to memorize it. S, we are told, is 500. N is 10, so the square root of n, 500 divided by the square root of n, that gives us 158.1139. So 158.11. Okay, so this is really sort of getting into steps 2 already, the test statistic. Actually, that was step 2. I've sort of gone a little bit ahead of myself. So the observed difference of the null hypothesis is, sorry, that's actually that's wrong there. Actually, it should be I overdone it a bit. I forgot what I was doing. Yeah, anyway, you get the idea. It's the observed difference divided by the standard error, okay? Which is the test statistic. That's the general construction of the test statistic there. Okay, and that works out to be, the test statistic there works out to be minus 1.265. Okay, so that's the test statistic there. Now the critical value is determined with alpha equals 5% and k equals 2. Okay, now k is the number of tails in the test. Alpha is the usual significance level. Okay, so what we're going to do here is go to our tables, and I use a particular type of tables called the Murdoch-Barnes tables. If you're not familiar with what I'm doing here with regard to the tables, just consult my other videos about this, or just actually sort of have a good look at how to look up tables from the student t-distribution. So I go to 0.025. Okay. I'll just be clear, this is I'm just doing a sort of facsimile of my statistical tables here. Okay, so I go to that column. Now the sample size is small, n is equal to 10, so that means the degrees of freedom is 9. So I go to row 9, or degrees of freedom equals 9. Okay, and in this case what I would do here is I'd look up my critical value, and that should be 2.262. Okay, so that is the critical value that we're going to compare the test statistic to. Now, if this is a large sample, we can use a critical value of 1.96. If we're dealing with, let's say, a sample size of 100, that would affect the standard error accordingly. Okay, but anyway. So, the decision rule is that the absolute value of the test statistic greater than the critical value is 1.265 greater than 2.262. No, we failed to reject the null hypothesis. There is not enough evidence to say that the mean is not 9,000 hours. So that's it there. Yeah, we'll leave that there.